The draw weight of a bow at full anchor is 65 pounds force. If at full anchor the string makes an angle of 55 degrees with the arrow, what is the tension in the bowstring? And there's kind of a picture here to help guide us what it's talking about there. So we have this bowstring here. Here's the nock of an arrow. The arrow kind of makes this angle of 55 degrees on both sides symmetrically. This line maybe could be a release aid. If you're into archery, you might know what that is. Otherwise, it's maybe representative of what the archer's fingers are doing, but in a very oversimplified manner. So I'm going with release aid because that actually might look like that a little bit, or part of it might. Anyway, so I think what I'd like to start with is trying to draw what I think is a free body diagram here. This is kind of a different example than we've looked at before because it's a little unclear to me, like, what object am I really considering and what forces? Like, is the arrow the object that I'm thinking about? And it could be, I suppose, but the thing is the arrow might be like resting on like a arrow shelf or something out here. Or maybe if it's a more primitive kind of bow, it could be on the person's hand or something like that. And I don't know if I'm supposed to think about that. Maybe a better thing to think about is like maybe the object is really like just a little bit of string right here that's being pulled back while at the same time these tension forces are pulling away from that. And if that's kind of my picture for what the system is, I would say here are kind of the forces that I see there. There's the kind of draw force, I guess you could say, the force applied by the archer through maybe a release aid or something else. And then there are these two tension forces that are kind of symmetrically oriented up and down at that kind of 55 degrees away from horizontal is one way of thinking about it there. So maybe I could call this one I'll call it FD for the draw force, and it's equal to the 65 pounds, force pounds. I'll say LBF here for that. And then these two, I mean, the symbols I put in the picture over here are T for the tension, but I'm going to prefer to call those, I think, FT, their magnitude, and maybe I can also say that there's a 1 and a 2 on that. I might need that in my analysis. Now, okay, given that the angle stated here is 55 degrees, I could look at this and say, okay, let's do this with a triangle type of analysis, but the triangle would not turn out to be a right triangle, and so it would be a little bit more difficult to analyze. So I prefer to do a situation like this, maybe based on components, just thinking ahead a little bit. But how am I going to do that? I mean, do I just start to work out like components of these forces? I think I need a bigger concept here. And the big concept is the concept of force balance, which is represented by F net being equal to 0. Oops, pen slipped a little bit there. There it is, which implies that the sum of the three force vectors that I'm looking at is equal to 0. Now, the trick I'd like to employ is, as we've been saying, if you have a vector equation, you can always look at a component equation. And maybe I'm going to look at the x components here, and maybe think about the components of each of these forces. So I know, like, let me draw kind of a dotted line out here. I know that there's an angle of 55 degrees here somewhere, right? Really, that's like 55 degrees, and as well symmetrically below here, there is a 55 degrees there. And that might help me to figure this out, because if I say, like, okay, FT1, which one was 1? I don't know, we'll make that the upper one. But if I want to know, like, what is the x component of that, that would entail taking this vector here and breaking it into vertical and horizontal components. And the horizontal component, I think, would lie adjacent to the 55 degrees. So I'm going to write the expression here, ft cosine of 55 degrees for that. The one that's below is similar. The horizontal component is also going to correspond to a cosine. Actually, hang on a second, though. Which way do I want to be positive? Maybe if I take a standard coordinate system, I should throw a minus on this, right? Because since this is kind of pointing in the second quadrant, the horizontal component should be negative, right? The x component should be negative. But the bottom tension force, Ft sub 2, is the same thing, because its vertical component points down, but its horizontal component points in the same direction as this one, basically has the same value. So I'm going to say minus Ft cosine of 55 degrees for that. And then FD, which is that draw force, is pointing in the positive x direction and has that value of 65 pound force. But I'm just going to say plus FD is equal to 0. And then I could look at this, and again, remember, this one is known, right? We know FD. And the thing I'd like to know is what this tension force is. And since it's symmetric, I've kind of assumed it's the same for both of them. So really, I just want to solve for that variable right there. So it looks like if I kind of combine things in the right way, right, this would be like minus 2 ft cosine 55 degrees plus fd is equal to 0. And now if I kind of like add this to both sides, but maybe I'd like to, I'm gonna leave the tension force part on the left here, but adding 2 ft cosine 55 to both sides would give me 2 ft cosine 55 degrees is equal to FD. And then I can isolate the FT by simply dividing by 2 cosine of 55. And now I always like to put off putting too many numbers in towards the end. You don't necessarily have to do that always as fastidiously as I do, although I recommend it. It gets confusing to have numbers too early because you tend to get lost in the units and the numbers really, really easily. But at this point, I'm feeling pretty comfortable to just say, okay, this is going to be 65 pound force divided by 2 times cosine of 55 degrees. And, you know, I've kind of left not enough space there to put the number in, but I can put all that into my calculator. And it says 56.662, etc. So maybe I'll just go up here and round that off to 56.7. And I've kind of kept everything just in pounds force. I mean, I could have complicated things by saying, oh, we have to go to newtons, but problem didn't tell me to do that, so I decided to keep it simple and not do that. So let's check our answer. There it is, 56.7 pound force, and the answer has taken the liberty of also giving us the answer in newtons in case somebody decided to try to tackle it that way.